BIM technology for analysis of large panel buildings in LIRA-SAPR. At first, let's talk about BIM integration of large panel building system. My colleague has explored with you the modeling analysis design technology in our program. The considered chain refers more to cast in situ reinforced concrete, because it includes the design stage. In addition to cast in situ structures, SAPFIR allows you to perform analysis of large panel buildings. For cast in situ building, the main purpose of analysis is the required amount of reinforcement in the load bearing elements. For analysis of large panel buildings, the stresses in the joint elements are our primary interest. How to generate design model for the large panel building? There are two ways to obtain a panel building in SAPFIR module of LIRA-SAPR program. The first one, to generate it directly in SAPFIR from individual panels. The second one, to use BIM integration through IFC file. In this case, you could import a whole building that should be cut into individual panels in SAPFIR module. You could also import complete model consisting of individual panels and only arrange joints there. The joint tool is available in a large panel building system. The main advantage of such system is the placement of joints in the model by automated tools. A panel joint is a parametric object of the model. It enables you to automatically generate appropriate analytical model for panel-to-panel connection. That is, at the same time get the model ready for analysis. For that, special finite elements of joint are implemented in LIRA-SAPR program. These elements are generated for the entire height of the joint and allow you to take into account for analysis the compliance of the mortar joint in the panel joint. The SAPFIR library of joints contains various types of joints, such as platform joint, contact joint, vertical joints of wall panels with and without embedded items. Linear and nonlinear analysis of panel buildings are available. For horizontal joints, the stiffness of finite elements is computed and sigma epsilon diagram is generated. It is possible to edit all parameters of joint or define a certain diagram for a joint. The program also computes bearing capacity per running meter of a joint in order to check compressive strength of horizontal joint. For a joint, it is possible to specify connecting elements of different stiffness. Such elements connect different number of panels, for example, embedded items slab to slab and slab to wall. The input data for computing parameters of the joint will be taken directly from the information model of the building. Material properties defined for wall panels and floor slabs are considered. The method for connecting panels and geometric properties, for example, wall or slab thickness, gaps, are both taken into account. Moreover, the user could define additional parameters, such as possible deviations of panels from the design location, non-uniform loading of the floor slab, etc. Information about bearing capacity of joint in short-term and long-term loads will be transferred directly to LIRA-SAPR in appropriate stiffnesses. The values of bearing capacity may be visualized as mosaic plots. SAPFIR module contains automated tools to generate BIM model for a panel building. At first, tools to cut walls and slabs into separate panels. Then, library of joints. The user could edit this library. Joints may be automatically arranged within the building according to user-defined library of joints. And the third, it is also possible to modify the settings of a joint located in the model. A wide range of parameters may be modified. The type of connection of elements, the thickness of mortar joint, the grade of mortar, the type and number of embedded items, and their stiffness. Then you could use the duplicate command to apply all modified properties to the joints of the same type. In the SAPFIR module, diagnostics of the arrangement of joints is available. The program will highlight places in the model where the panels are not connected by joints. The tool that provides automatic tags for joints enables you to display max information about the joint in the tag. For example, joint orientation, scheme of connecting of panels, number of embedded items, and so on. The schedule of joints presents the summary table with information about number of joints in the tag. The schedule is interactive and may be used to modify the properties of selected tag of joints. Joints are displayed on the 3D model and on documentation views, plans and sections. It helps you to check arrangement of joints in the BIM model and with visual orientation. Certain color is selected for the joint according to the assigned tag. This color is displayed in the analytical model and on documentation views. Joints and their parameters may be modified on plans and sections as well. Now I would like to show you a video. We will see how the joint behaves and we'll see the tools that were discussed earlier. Let's take an architectural model with dimensions equal to dimensions of wall panels on floor slabs. We could keep an eye on the analytical model. The joint toolbar has tools to cut the slabs and walls. For example, we will fragment the last story and will make several cuts of slabs. We can also make cuts of walls. Then we open the library of joints. You could add your own joints with specified indents, arrangement of embedded items, ways of connecting objects to each other, color indication of joint, its tags, so you can add this to the library and use them in other projects. To place the joint, activate certain tool and place the pointer at appropriate objects. The type of a certain joint is shown dynamically. If the joint cannot be placed, it is colored red. In this case, the vertical joint is colored red because the end walls have interpretation as the load bearing structure and the facade wall has interpretation as the load. Let's select this joint, duplicate it and indicate where to place it. In this case, upward along the branch. You could configure several joints on the story, and then duplicate all of them at once to the entire building. It is also possible to apply the joints to the whole structure. In the appropriate dialog box, I define which joints I want to create, where to create them, etc. Then the program will create all joints, even at places where we cut the panels manually. In the Schedule of Joints dialog box, you could check all joints and even edit them. Here you could check the computed stiffness values for the finite elements of contact joint. It is also possible to check the values of long-term and short-term bearing capacity of joint. For the vertical joint, arrangement of embedded items and the stiffness per running meter of these embedded items were defined. The next step is to transfer the generated structure to the finite element model, where we could define the type and step of triangulation. It should be noted that the type and step of triangulation might be defined separately for each object, either wall or slab, in the properties of this object. After triangulation, we will see the finite element model. You could evaluate the quality of the model before transferring it to LIRA-SAPR module. Then the generated data will be transferred to LIRA-SAPR for analysis. And here we can see all the stiffnesses for elements and joints that have been formed in the SAPFIR preprocessor.
Peculiar features for analysis of large panel building. Important notes about finite elements of the horizontal joint. First, By default, the nonlinear stiffness of the joint in finite element 258/259 with 3 pairs of sigma epsilon values is transferred from SAPFIR preprocessor. Second, if the history of nonlinear load cases is not defined for analysis, then the joint behaves linearly along the first branch of the diagram for all load cases with the same stiffness. Third, if the load history is defined, then the joint behaves nonlinearly according to the specified 3-linear diagram. Fourth, in nonlinear FE of joint, the vertical stiffness is determined by a 3-linear diagram, while the shear stiffness in and out of the plane of the panel depends on the stress-strain state of the FE along the vertical. If the FE is in compression, then the shear stiffness is taken according to a specified shear modulus G, and if the FE is in tension, then the shear stiffness is equal to 0. Fifth, since the FE of the joint is step type 1, the maximum tension in the joint is proportional to the step. The smaller the step, the less tension will be obtained. The figures show the analysis result in terms of vertical stresses of the joint above the opening in the wall panel. A. Linear analysis, B. Nonlinear analysis in 10 steps, C. Nonlinear analysis in 100 steps. Nonlinear finite element of joint. Iterative finite element is available in LIRA-SAPR software. Figure 1 shows the compressive stress-strain diagram at joint. Stiffness is computed for each section of the diagram. Stiffness depends on compliance that is computed according to building codes. The shear is considered for the FE of the joint. For the iterative FE, there is dependence as presented in figure 2. The shear stiffness is changed from 0 in an uncompressed joint, i.e. neutral, no compression or tension. Then the shear stiffness tends to a maximum in a user-defined value at the point sigma m1 on the compression diagram, and tends back to 0 at the point sigma m2. This describes behavior of the iteration element. And a slightly different dependence for the step type FE. Figures 3 show its behavior. That is, there will be a sudden change at first. For a tension joint 0, for a compressed joint the ultimate value is constant and max up to the point sigma m1 and then decreases to the point sigma m2. Why is it so important to get proper behavior of the joint in shear? In the case the fragment of the joint will not take shear loads, the total bearing capacity of joint in shear will be less. And this should be taken into account. Since the fragment of the joint may be tensioned or compressed too much, then these fragments of the joint should be excluded from behavior of joint in shear. That's why the remaining fragment of the joint will take a greater load. If it is necessary to impose additional shear elements in this case, it is necessary to obtain the correct loads on these additional elements. The book RC Walls of Earthquake-Resistant Buildings describes the design experience for load-bearing monolithic and panel RC walls during earthquake in various countries. Therefore, we applied the data from this book to verify the behavior of iterative FEs. Test examples in statics and dynamics. Let's compare results of iterative and step-type analysis. For the step-type analysis at the top, we define 20 steps. For iterative elements at the bottom, one step is defined. Then nonlinear analysis is carried out. We obtain the following. Despite quite a lot of steps, 20, in the step-type nonlinear problem, there are areas with tension greater than 0 and areas of maximum compression that exceed the ultimate value specified in the input data. In iterative nonlinear analysis, everything is quite accurate. The tensioned elements are 0, while compressed elements are 946 square ton meter, as it was specified in the input data for the third part of the diagram. Let's compare the distribution of compressive stress in the joint along the length of the joint for the iterative problem. From left to right, two variants of the axial loading of the wall panel, so the joint is uniformly compressed but with different intensity. Below and above the breakpoint on the compression diagram. The rest of the examples are chosen so that to compare them with the standards from Ashkenazy's book. Main conclusions. The limit value of 945 tons per meter in squared is not exceeded, and in the place where the joint is tensioned, the forces have 0 values. Let's compare the distribution of shear stresses along the joint. At the end parts of the joint, the Qx is not equal to 0, since the stresses in the FE of joint are calculated at its center of gravity. Here you see the distribution of shear stresses in horizontal joints, and if you compare it with the standard one mentioned in the book, then they converge well. For example, in the rightmost joint, shear stresses arise only in the part of the joint that is not tensioned or compressed to the ultimate value. Conclusions. First, in iterative FE, the ultimate stress values more accurately coincide with the values in literature. Second, shear stiffness obtained with iterative FE provides shear stresses distributed along the joint. These stresses are similar to those described in the literature. This design model is provided by PIC Project Company. We will use this model to compare the speed of LIRA-SAPR with a count of different analysis settings. Quite an interesting design model. This is a 33-story panel building. Here in the design model, more than 1 million nodes and about 1 million elements, of which there are 32,212 Nonlinear FE 55 and almost 100,000 FEs of the joint. The analysis type with iterative FE was 73 minutes. Iterative FE of the joint provides one more advantage: direct integration in time, Dynamics Plus. It will enable you to carry out earthquake analysis as accelerogram or solve the problem of dynamics local failure, progressive collapse. Let's make a test problem. A two-dimensional post of wall panels with a count of assemblage and defined accelerogram along the x-axis. Here a horizontal bar is located in the element of joint. This is simulation of the floor slab to which the load will be applied. FE 255, these are two node elements that connect the wall panel with the bar, with the floor slab and with the overlying wall. The problem is considered with a count of erection and the specified accelerogram along the x-axis. Let's see how it will behave in direct integration in time. After time history analysis, only previous history is available in analysis results. That is, the total stress strain state from the load history that preceded the dynamic load. We would like to see the analysis results at different points in time. Select appropriate option in the integration step menu. In the drop-down list we get analysis results, the compressed joint, the shear forces at joint, and so on, and all other forces and stresses. Let's use another method. We will look at the element of joint with the information about element tool. Select the time history analysis option in the dialog box and we will receive appropriate graph. On this graph you could easily select peak values. Peak in shear, in compression, min in compression, max in shear. We've fixed appropriate moments in time. Then close and evaluate our design model at selected time points. That is all types of forces that we have in analysis results. Or start the animation of vibrations. For example, we will visualize displacement along the x-axis. Here we put 0 and press start. Displacements will be changed in time along the x-axis. Right in the visualization process we could activate another factor, for example compression at the joint. Now we see behavior of the compressed joint in dynamic load, or shear forces. Their sign depends on behavior of the structure, or let's say forces in additional elements. Then enhance visualization of mosaic plots. Additional element will take the shear in one direction, then in the other direction. The sign is changed. That is, it may be visualized in detail. Let's see the results for the animation of vibrations. Activate this option. Here you can see the behavior of horizontal joints. With a max slope in one direction, on the opposite side the joint will also be in tension. NZ elements will be in a compression respectively. Look at the NX force. We see that the horizontal forces are not maximum, and they are concentrated about the place where additional elements is located in the horizontal joint. This is an X horizontal and Y vertical. We see the high forces along Z axis in places where additional elements are located in the vertical joint. In conclusion, I would like to get off the subject about features and options of our software and introduce you to a practical example of modeling a large panel building with the all-plan SAPFIR LIRA-SAPR integration. Here you will see the fragments from the presentation made by our big client, the Betotech project company. Let's take one of their projects. A 9-story residential large panel building with a planned size of about 40 meters by 13 meters in excess. Lateral and longitudinal walls are load-bearing ones. Massive floor slabs supported along 2, 3 and 4 sides. Also there are platform and contact joints. Several advantages of using the integration all-plan SAPFIR LIRA-SAPR from our users. All plan premises are converted in SAPFIR 3D spaces, user-friendly presentation of loads, actual location of partitions is considered, export of objects of different forms, all plan SAPFIR 3D. So LIRA-SAPR provides a full range of options to analyze a large panel building using a BIM model from any software. To evaluate our program, we recommend that you use either the demo version or LIRA-SAPR 2016 R5 non-commercial version. Both are distributed free of charge and available on our website for download. That is all from us. Thank you for your attention.